So, good morning. I am Krishna Kumar from Krishna's classroom. We continue with the discussions on the matrix representations of linear transformations on finite dimensional vector spaces. Now, in the last lecture, we have seen that the matrix representation is not uniquely determined, and this is a consequence of its dependence on the basis that we choose for the domain space as well as for the range space. So by changing the basis, we can get a different representation. Now this is what we have observed. Now let us explore this further. So let me start with our basic assumptions that V is a vector space of dimension n and W is a vector space of dimension okay. Now we have also fixed the basis, so let we call our notation ordered basis V and BW these are the basic notations, and look at this word order, and we said that the order in which the elements of the basis are arranged is important. If we change the order, the representation also will undergo a change. So that is the central problem that we face. It's a multitude of representations possible for a linear transformation. Now we have, so let us try to picture this. Okay. This is V, this is W. Now you have copy of Fn. Then you have chosen a basis BE corresponding to BB. You take a vector V is mapped to some vector X, and then P maps B to B. Now this is mapped to some Y. The relation is this, that fix the notation. So we have the ordered basis W. So all this discussion is with reference to the ordered basis BV and BW. So we have now, if V has a unique representation, Xn VA, and we write x to be xn. Similarly, PV is a linear combination of something like y1 w1 ym wm, and we write y to be ym. Okay, so this is your y. Now you look at this as a column vector, this also is a column vector. Then we have a matrix connecting them, or we define a map which maps x to y, and we were looking at the status of that, and we found that this is represented by a matrix, by a m by n matrix A, right? And of course, given T and having fixed the basis for V and W, you are asking what is going to be the representation for this. We get a matrix representation A, right? In fact, strictly speaking, since we explicitly compute as a matrix representation, it is clear that it's a linear transformation. But let us see how this independently. Okay? Right? Realize this independently. Now you see that corresponding to the choice of VV, there is an isomorphism from V to Fn denoted by phi. And corresponding to the choice of the ordered basis VW, there is an isomorphism psi from W to Fn. Okay, this is both phi is one-to-one, onto, and linear. So also psi is also one-to-one, onto, linear between W and Fm. Here it is from between V and Fn. Now these are the basic facts that you have. Therefore, you see that both phi inverse is defined from here back to this place. So also psi inverse defined, and both phi inverse and psi inverse are also one-to-one, onto maps between their respective domains and the ranges, and they are also one-to-one, onto. So that's the property of the isomorphism. Now you see that from this diagram, it is quite clear that what is A? See, you have AX equal to Y. This is the picture that you have. On the other side, you have TV equal to some W. If you want, you denote this by W. And A depends on the choice of the ordered basis. Now you see that A of X I can write as what? See, I can go from Fn to Fm through this another route. And what is that route? So I get this as if I apply phi inverse of X, I get V. And then apply T. Then what I do is I map with So this is the map that I have. Okay. So A is essentially psi composition, T composition, phi inverse. And you know that phi inverse is linear. T is linear. Therefore, T composition phi inverse is linear. Now, psi is linear and the composition map is also linear. Okay. Therefore, now this is linear. Since phi inverse T so that's a very quick proof of the linearity of A. Therefore, the association that we have defined between X and Y is a linear map. So that is one observation. Now we make some further observations about this. So this is second observation. Third observation is we also make a little more elaborate this. You know that what we have is this TV is equal to sigma I equal to 1 to m A sigma j equal to 1 to n Aij xt. This is the relation that you have basically. So that connects T with Aij or A. So A is the m by n matrix. Now let us start. All this depends on both BV and BW. Now let columns of the matrix that means you have got A11, A12, this is your A. Now you see that this is the first column, A1, this is the second column, this is the nth column. So jth column is given by Aj. Now we look at what Aj is. Aj is essentially T Vj, the matrix representation of T Vj, that is with reference to the basis BV So how do you get that? So set PV. Now, what happens to this? Now you see that V equal to Vj implies what are the images of Vj? The images of Vj are the following, that is xi equal to or you will get this in turn, you will get this as the following. For more explicitly, I can write it as you have xj equal to 1 and xi I naught, where what you have is that V is identified with or we'll say that the representation of V with respect to BV that's the definition that we have. This is the relation that we have. Okay? Therefore, now we compute TVJ. So, what about TVJ? Just set here. So, you see that xj equal to 1, but for all other values of j, it is 0. Okay? Therefore, you get TVJ is computed with respect to this is equal to keep all these basics in mind. Keep this figure for the time being there. Okay. So what you have is that TVJ, this is equal to sigma I equal to 1 to m Aij W1. Therefore, TVJ with respect to BW, this is equal to given by It is, if you write it up, if you fix J and write it up, this is equal to A1J therefore TVJ is this is equal to this I write as so AJ is the jth column of or I can write A as n columns. That's the notation. So now we compute further. I hope it is clear. I treat the picture as it is. Now let us start working on CA plus, okay, two operators. Let and represented by an m by n matrix B, which is given by and the columns of B are given by B1, B2, etc. Here. Okay, these are m vectors. I mean, each one is an m vector. Okay, right. Then we have CA plus B CP plus S. Okay, with respect to the ordered basis BB and B. That is the representative. And we prove this for, so we are going to prove. We are going to prove that statement for CAJ plus BJ. This is equal to CPBJ Okay. That is coming from that. So we have made this analysis. Now that is equal to, so these are column vectors. This is equal to CPVJ plus S Now this is equal to Ct plus S. BW. What does it mean? Means that the jth column of the matrix representing Ct plus S is given by Caj plus Bj. By Caj plus Bj. What does it mean? It means that CAB, that is represents S with respect to the, so that completes the thing. Now we make an observation. So now you have got, this is T is an element of L W and A is an element of okay. Now we define a mapping from LVW to M cross and F. How do you define it? Associate A with T. Okay. So let here. And what we are going to prove is that this is an isomorphism. You know that this is a linear space structure. This also is a linear space structure. This is of dimension m. This is also of dimension m. Now what we are going to say is that there is a isomorphism related to BVBW of LBW onto MF. So this is what we are going to do. Let and WB and M dimensional vector space let ordered basis of B and W respectively. Now then there exists chi defined from L E W to F by defined by chi of t equal to A, where t and A are as described earlier. Okay. Which is an isomorphism of onto that's a beautiful thing. Okay, I mean, you know that all the preliminary requirements for this theorem to be plausible are there, because this is an Mn dimensional vector space, this is also an Mn dimensional vector space, so they are anyway isomorphic. But what we are going to say is that this actually gives an explicit isomorphism. And this isomorphism is related to the choice of dV and dW. So this is an isomorphism. Chi is dependent on BW, because that actually essentially connects T with the particular A. If you change the ordered basis, then it is going to be another matrix that is going to be representing that. Now once again let us go back to the picture. What do you have? So we want to say that given T there is an A. That is clear. Okay. How is A defined? A is defined by C. Then we have the corresponding ways. Matrix A determined by the choice of BW. Okay, and we write chi of A. This is the connection that we can establish. So we want to show that this is an isomorphism. Okay, so what are the things that we have to verify? So this is your thing. So given T, how do you get your A? So given T, A is equal to phi inverse of T set. So phi inverse of set. This is your A. Okay. And you know that if T is linear, of course A is linear. And you can show that T1 minus T2 T1, if T1 is not equal to T2, then A1 is not equal to A2. Okay. So you check the following. Leave it you to check this. Our definition is this: chi of this is the definition. Okay. Now we observe that chi of T1 plus T2, this is equal to psi of phi inverse, and this is equal to psi of phi inverse. That is because psi is an isomorphism. Therefore, you see that if you start with any v here, then this is going to be so. Or more explicitly, one should write like this. No, sorry. I think. X. Okay. Right. So phi inverse of x is equal to v. So this is equal to psi of t. Now that's equal to psi of T2. Okay. And what is that? That's equal to psi of T1 plus psi of T2 B. And what is that? That's equal to chi of because once again you can write this as phi inverse of x, and then phi inverse you combine with this. This is. So if you want, you can write one more line. So this is equal to psi of T1 plus T2 is equal to this is true for every x. Therefore, chi of T1 plus T2 implies similarly show that chi of sometimes for every t in LBW. So chi is linear. So chi is now show that chi is 1 to 1. And since chi is linear, it is sufficient to show that once chi is 1 to 1, it is also constant. Okay. So how to show this? So we start with chi t of x. Belonging to x belonging to does this mean? This means we work this out. Chi t is equal to A. That is the Ax which implies A equal to 0, of course. Now, what is the relation between A and T? Okay. Now you see that A is equal to sin t phi inverse. So this implies sin t phi inverse is 0. Okay, that's a zero linear transformation or zero matrix. What does this mean? This means that since both psi and phi are 1 to 1, so you see that this is equal to so you can work out t. What is t from here? See, you can see t. What is t? T is actually equal to phi on one side, then A, then psi inverse, okay, which is equal to, now if A is the zero matrix, then P is equal to psi inverse 0 operator phi, which is equal to psi inverse of 0, which is okay, which in turn implies P equal to. Now this needs little bit of elaborate writing like this if you like. So that is quite simple. Therefore, chi is 1 to 1. And dimension of what? LBW equal to Mn. This is also equal to dimension of M which implies chi is also 1. Therefore, chi is an isomorph. So we are identifying LBW with the whole of M cross N F. Okay. So this is one isomorphism, and this particular isomorphism chi is completely dependent on the ordered basis that you choose for V and W. So let us just put that once again to affirm the whole thing. So I want to put this in your mind. Remark this isomorphism is dependent on choice of the consequence is that given T, it is represented by several matrices from M cross N, F, which depends on the choice of the ordered basis for V and W. Okay? Right? So this information let us keep in our mind. We will come back to that later. Now we will possibly look at a special case. Which we often come across. Then dimensional NC. So both the domain and range are now the same. Then LBW is denoted by L. That's our notation. And this is a dimensional, is an n square dimensional. Vector space over. So we are now interested to look at T belonging to Now we have already seen that if you have three vector spaces, finite dimensional vector spaces, say U, V, W, then we can talk about the composition of linear transformations. So since so we are only interested only on LV. Now on LV, we can compose linear transformation both ways. That means if T belongs to LS, LV, S belongs to LV, then both TS and ST are defined, and TS LV, ST also belongs to A. However, they may not be equal. May not be equal to ST. Okay. And we have the advantage to choose, let us choose the same basis. The domain as well as range. As well as range. This is an advantage that we have. When both the domain and the range are the same spaces. That's an advantage that we have. So henceforth we fix dimension of V equal to n. VV we choose as the ordered basis. And T belonging to LV pick up. Then what we have is the following. That is, we have TVJ TI, and therefore the matrix of T with respect to B is given by A. It's an n by n matrix. Then we have more. We have the TVJ with respect to B is given by B. Okay, we can write here. This is B is the only thing that is important. Okay, right. Now see that therefore TV with respect to the basis is given by this is something you can easily do. Okay. So we call this A, then this corresponds to the following that you have. actually a into x. Now we look at some examples. We take V to be let A be the be a fixed matrix over F. Then A is equal to Aij. This is the matrix. Now define A from P from V to W by Tx so what is W? W is then the W is so let analogous to the standard basis Fn cross 1 given by xi this is the column vector with ith place equal to 1 and all other places equal to 0. This is the standard E1, E2, etc. Again written in the column form. Okay. So what you have then B, the ordered basis B is given by xi. Let corresponding ordered basis, which is equal to delta. What is that? Yj equal to then what you have is that BW is given by, in this case, then the matrix of T relative to BW that's what we have. So in fact, this is what you have. You have A11, 1, 2, etc. A10, AM, A. This is your A. This is your A. This acts on this corresponds to jth element. This is equal to the jth column. Yeah, this is the jth column. This is A1, this is what we get. Okay, so this is the connection rate. So the columns of this matrix A, if you take the standard basis, then for the domain space and the standard basis for the range space, then the column, the jth column will give you the image of the jth element in the ordered basis. And so that's the first example. Just a routine one that whatever we have done, we have now done for matrix operators. Take an example, second example. Let us take the B to B operator. Take T of something like projection operators. We take E1 to be 1, 0, E2 to be 0, 1 as the basis for B. Then you calculate TE1 equal to, by definition, it is 1, 0. Okay? It's actually T of 1 0, which is equal to 1 0 itself, which you can write as 1 times E1 plus 0 times E2. Similarly, TE2 you calculate. This is equal to T of 0 1. This is actually 0 0, which is equal to 0 times E1 plus 0 times E2. Therefore, what is the matrix representation for? Therefore, T with respect to that is the, so this column first column, and these two elements represent the second column. Third example. Third example. This is on, here we take V to be all polynomials including the 0 point. Then dimension of a typical member of P belongs to, then Px is of the form P0 plus x cube. That's a typical member. And now we choose the basis. Now let us choose the ordered basis. Four, where the polynomials. Equal to x cube. So we define the transformation d from b to b as the differentiation operator. What does it mean? It means now let us compute the action of D on F1, F2, F3 and F4. So dF1 is then equal to 0. dF2 1, dF3 equal to 2x, dF4 x square. Now let us write this. This can be written as 0 times F1 plus 0 times f2 that is a unique write-up or breakup of df1 in terms of f1, f2, f3, f4. And this is equal to 0 times f1, 1 times f2 plus 0 times f3 plus 0 times f4. Now this is equal to 0 times f1 plus 0 times f2 plus 2 times f3 plus f4. Now this is equal to 0 times f1 plus 0 times f2 plus oh sorry, I think I written it wrong. It is 1 times f1 and this is equal to 0, right? This is 2. Now this is equal to, okay, this is equal to 3 times f3 plus, okay, therefore the matrix of D with respect to the basis that we have chosen is given by, let us write it down. What will happen? What will be the first row? The first row is going to be the coefficients of f1 in this, written in that order. So it is going to be 0, 1, 0, 0. Then you have 0, 0, 2, 0. The next one is 0, 0. And then you have so this is the matrix representation of D with respect to, okay. Right. Now we continue our exploration. So these are the 3 examples that we looked at, and you can give many more examples at this kind to work on. Now we start with our basic assumption that there are 2 matrices. Suppose V is a vector space, and then so we have, if A represents B prime and B represents gives the matrix of S. Let me write here consistent. W. Then one can prove that the A plus B so also CA so this is some of the things that are easily verified. Okay, now we talk about the matrices of the composition. Okay, so let us take the following scenario. Namely, you have now three vector spaces. Okay. So you have U, V, W. Okay. Now the dimension of this is taken as n, this as m, this is a dimension p. So we have a basis B here, there is a basis B prime here, there is a basis B W prime. Okay, so let us write down. Let finite dimensional vector spaces over F of dimension n, m, and p respectively. So let B WP be the ordered basis for U, V, W respectively. We fix that. Okay, choose these three bases. Now we have so let then what you have is this TU, the basis with respect to B prime is equal to A times basis with respect to B. This is the summary of what we did. A represents okay. Then what we have is S EU B double prime. This is equal to B of B prime, which is equal to B A of UB. Okay. Therefore, if C represents the matrix representation of ST U to W, then by uniqueness representation, we have C equal to U. That is, C is essentially double prime. So this is the relation. That comes now. Okay, so you have STU B double prime is also equal to, so this is one relation, STU B double prime equal to BA okay. The same relation as you have. Okay, sorry. But you have these two relations. Therefore, so this is the reason for it. And this is also there. That is, this is equal to this. This is another relation. So using 1 and 2, you get this is equal to this. So let us work it out. If you want, you can work it out. You have ST of UG. This is equal to S of U. And this is equal to U of sigma A equal to 1 to N AKJ B2. And that's equal to sigma AKJ K equal to 1 to M AKJ AKJ This is equal to sigma k equal to 1 to m akg sigma I equal to 1 to p d. This is what we are writing. This is exactly, please follow the symbols like this. And that can be rewritten as, because all finite sum 1 to p, you have sigma k equal to 1 to m dik akj therefore which implies, or this I can write as this is essentially same as sigma I equal to 1 to p Cij wi, which implies and that gives C equal to this is the consequence. Therefore, you can write down here let vector spaces over of dimension n p respectively. Let LUB LBW as you have seen here. If B prime, B double prime are ordered basis of U, V, W respectively. And A is equal to right? The matrix representation of with respect to B prime, B double prime, and ST, the matrix representation of double prime equal to DA, which is equal to the matrix representation of S into the matrix representation of T that's the theorem that we have just now verified. And you see that this is U, this is S of A. Now you have got this connection. You have suppose we denote this by X, this will be denoted by Y equal to A X, then this equal to B, this will be X. Okay, so what you have is this. See, you have T map to U map to ST. Here, correspondingly, this is mapped to, this is mapped to, this is the operator. That's the corresponding relationship that we have. So whatever is happening here, there's a corresponding thing happening there with the matrix. Now this is the advantage of matrix representations. Now I think from next time I will introduce what are called invertible operators and also say something about change of basis, because we have already said that if you have two different bases, okay, once you change the basis, the matrix representation will be different. This is something that we know already, and therefore we will have to work with that idea. And then also it's natural to ask how the change of basis is affecting the matrix representation. How are they connected through the change of basis? And can you describe this explicitly? And that's a very interesting question that we have to ask. Okay? And this will connect the different matrix representation of the same linear transformation, how they are connected, and how they are connected through the change of basis. So, thank you very much.